Welcome to the part 2 of Cloud Auto Scaling series. In part 1, we understood the basics of latency and what happens when a single server gets overwhelmed. Today, we take the next major step, distributing traffic across multiple servers using load balancing. This is where cloud application starts becoming scalable in the real world. Whenever you add more servers, the first question is how do you decide which server handles which requests? That's where a load balancer comes in. A load balancer sits in the front of all your servers and evenly distributes incoming traffic. It prevents a situation where one server becomes overloaded while others sit idle. Most importantly, it helps maintain low latency and high reliability during traffic spikes. Scaling out or adding more servers is only effective if traffic is actually shared between them. Without a load balancer, even if you have 5 servers, all traffic would still hit server 1 and nothing would improve. The load balancer acts like a traffic manager. Every incoming request passes through it and it decides which server should handle that request. This is what makes horizontal scaling possible. One of the simplest load balancing algorithms is round robin. It assigns each incoming request to the next server in a loop. Request 1 goes to server 1, request 2 goes to server 2, and so on. This method assumes all servers are identical and all requests take roughly the same time. When workloads vary, round robin may give extra load to already busy servers. Least connections is a smarter and more adaptive strategy. Instead of distributing blindly, it checks how many active requests each server is handling. Then it sends the next request to the server with the fewest active connections. This balances the load more accurately and ensures no single server becomes a bottleneck, especially when some requests are heavier than others. These strategies are not just theoretical, they power real cloud platforms. AWS uses Elastic Load Balancers, Google Cloud and Azure have their own global load balancing solutions. In self-hosted environments, NGINX and HA proxy are extremely popular. Almost every modern scalable application on the internet uses some form of load balancing. In this part, let's use our simulation to visualize load balancing. I'll temporarily turn auto scaling off and start by creating a few servers by increasing traffic. Now that multiple servers are active, you can see how the load distributes across them. When using a round robin like behavior, load spreads evenly in a simple sequence. But when we switch to a least connections like logic, the simulation adapts to real time server load, giving more work to the server that at least is busy. Even with the simplified visual model, you can clearly see how load balancing prevents any one server from becoming overloaded too quickly. Load balancing distributes load, but it doesn't create more capacity. If traffic becomes so high that all servers are overloaded, even perfect load balancing won't save the system. All servers will turn yellow or red, indicating rising pressure. This is why we need auto scaling to add more servers dynamically. Let's increase the traffic further to simulate a heavy spike. Now notice how all servers eventually show high load. The latency graph starts rising sharply because even there or 4 servers aren't enough. This is how real systems detect bottlenecks and initiate auto scaling. Load balancing is essential for horizontal scaling. Round robin is simple but doesn't adapt. Least connections is smarter for uneven loads. Load balancing alone can't handle the massive spikes. Auto scaling plus load balancing together form the backbone of cloud scalability. In part 3, we will bring everything together: triggers, scaling rules, cooldowns, and full real time behavior. Thank you.